Okay, so as I told you, we'll be following one material, okay, because it's easy to follow one material. Now, what we'll be doing is we'll be covering all the important concepts. Anyways, I'll be covering all the concepts. I'll just highlight that which concept is important, in which concept more question is asked, right? Because this chapter is one of the easiest chapter when you talk about NEET or JEE. Okay, most of the question that will be asked will be either formula putting getting or concept or a simple concept based on simple concepts, right? Now, let's start with this chapter. Now, when we talk about this chapter, can you tell me how many, this chapter can be divided in how many parts? Tell me guys, this chapter can be divided in how many parts? So 3 to 4 parts, right? 3 to 4 parts. Okay. So basically I will consider 3 parts. The first is your basic calorimetry, right? Which I think that I need not to teach calorimetry. I hope everyone know heat gain is equal to heat loss, then heat exchanges, MC delta T and all those things, right? Then second is your thermal properties, which is basically your heat transfer, right? Thermal properties. So this you can divide into 2 parts, right? It is your heat transfer and expansion, thermal expansion plus heat transfer. Got it? Right? You should have a mind map. Okay, whenever you have a mind map, it will be easy. Now, when you talk about heat transfer, in heat transfer, right, we have different topics. The most important is your conduction, right? Then radiation, then Stephen's law, right? Wind's displacement law, right? And Newton's law of cooling. That's it. So we have basically 5 major topics in this heat transfer. Okay. Now in thermal expansion, we just have expansion. And if you want to take this topic to other level, then we will use the stress strain relationship of properties of solids and we'll combine it with thermodynamics, right? That will be a higher level problem, okay, which will be mostly asked in either JE or advanced, right? But thermal expansion is comparatively easy one, okay, unless and until you are mixing this with your property of solid. Now the last chapter is your thermodynamics plus KTG, right? So this chapter is 50% same as chemistry. Yes or no? Tell me. Theory wise, it's completely same as chemistry, right? Problem wise, it is different. Okay. So we'll be covering mainly these 2 topics. I'll be covering calorimetry and theory wise, but we won't be focusing more on the problem solving because this is quite easy and hope all of you know how to solve problems in calorimetry. Okay. So now let's start, right? Let's start with our class. Okay. Now, when we talk about, I'll just go through the basics. I'll just go through the same material so that we don't leave any topic, right? So I hope all of you know the temperature scale, the conversion of one unit into other unit. The unit is this, right? When you talk about the formula, this is just this one, right? Unit minus lower limit by upper limit minus lower limit, right? This is the basic formula of conversion of any one unit of temperature scale, which is degree centigrade, Fahrenheit, or Kelvin, into any other scale, right? Now, there's one question which is asked a lot, right? Based on this, that at what temperature this Fahrenheit and Kelvin are same. I hope all of you already know this, right? But this is one question which is asked many times, which is minus 40 degrees centigrade, which is based on this concept, right? So if you talk about, see, whenever you are revising, think about what kind of question can be formed on any concept. Then everything will be easy and you will be able to solve all the kind of problems. Okay. Now, after this concept, right? Wait, what is happening? Okay. Yeah, you can see, right? The type of question which can be asked in this concept, just write it down. Concept 1, which is temperature scale, is your conversion of one temperature scale into another temperature scale, right? That's very easy. So level is easy. Now, when you talk about next, So next is your thermal expansion, okay, which I talked about, thermal expansion, because we are ditching calorimetry. Now, when we talk about expansion, so we know that when any matter is subjected to heat, right, which is subjected to energy, then the molecules or the atoms, right, gain energy, right? And we know that whenever any atom or any molecule gain energy, they start vibrating, right? The energy increases. Yes or no? The kinetic energy increases. Now, because of that, right, they try to move away from each other, because obviously they'll oscillate, they'll vibrate, okay. That is the intermolecular level, like on intermolecular level. So obviously that might result in the change in shape and structure of any substance. Yes or no? Right? The easily understood part is in gases. We studied that when we talk about gases, we use ideal gas equation, which is PV is equal to nRT, right? So we studied that when we increase the temperature, the kinetic energy increases, and when the kinetic energy increases, the molecule travel faster, increasing the volume, right? And if we keep volume constant, then it will increase the pressure. So we can use the same concept in your solids or liquids. Now, when we talk about solids, so we have three parameters, right? Which is length, area, as well as volume. Okay, so when you talk about expansion, we can have three type of expansion, right? When you talk about just length, it is your linear expansion. The formula is given by L is equal to L naught 1 plus alpha delta T, right? Delta T or delta theta, where alpha is your linear coefficient of expansion. Okay, so if you take this to this side, it will be delta L is equal to L naught alpha delta theta. The question based on this concept will be very easy, very easy. And if you think about it, right, you can mix the concept of stress and strain, right, with this. Okay, think about it. Think like like a teacher, right, who can make a problem. Okay, so if you think like that, then you will be able to solve all the problems, right? What can they use? They cannot use anything else. They can just use either this straight formula putting getting questions or mix it with stress and strain. Okay. Now, next is superficial or area expansion. Now, when we talk about superficial or area expansion, it is the change in overall area, right? So ultimately, when you talk about the overall area, it is length as well as breadth. Okay, so I can say that, okay, so we have length increase as well as breadth is increased, right? So area is length into breadth. Okay, so I can say that let the initial area be L naught square and final area is L square or L into breadth, right? We are taking square for our convenience, but we can take any surface, doesn't matter. So the formula which we will see here is, right, when you talk about 1 plus alpha delta t whole square, so it will be 1 plus 2 alpha delta t plus alpha delta t whole square, but this coefficient of expansion alpha will be so less that will be neglected, right? So we'll be left with 2 alpha delta t. Okay, right? Now this 2 alpha is called as beta, right? So I can just say that it is A is equal to A naught, A naught 1 plus beta delta t, okay, or beta delta theta, where beta is 2 alpha. That is the relationship that you should know for the same material, right? This concept is for same material, okay, because alpha, beta, and gamma are the material dependent. Now volume expansion, same, right? Whole cube, if you make it cube, we will have 3 alpha beta into 3 alpha square plus beta square, right? So if you consider this and neglect the coefficients, okay, so we will get this v is equal to v naught 1 plus gamma delta t, where gamma is equal to 3 alpha. So the ratio of alpha, beta, gamma for same material is 1 is to 2 is to 3. Now, when you talk about problem based on this, right, based on volume expansion, so you can use bulk modulus, right, in this concept, nothing else. Okay, or simple formula putting getting. Okay, now when you talk about the application, we have already studied, when you talk about the application, we can use, right, the concept of stress and strain. So this is very famous question that we have already solved, and that is present in almost all the textbook, which is bimetallic strip, right? Right? So in bimetallic strip, the coefficient of expansion will be different. So if the coefficient of expansion will be different, their change in length will be different, right? And because of that, there might be strain on the object. So they will be asked to find, right, what is the change, what is the deflection, what is the strain, right, all those kind of information. Okay, so I hope by using the concept of stress and strain and this change in length, you can find it. Okay, the second application, right, when you talk about the second application, what can be the second application? Tell me, anyone, right? Is the change in time period, because when you talk about simple pendulum, what is the formula? Tell me, what is the formula? I hope everyone remember 2 pi root L by M. Tell me, for pendulum, yes, sorry, root L by G, right? 2 pi root L by G. So obviously, right, if temperature is increased, length will change. Okay, length will change. So when you talk about change in temperature, sorry, change in time period. So change in time period is given by 1 by 2 root, sorry, root will be converted in 1 by 2 delta L by L. Okay, and this delta L by L is nothing but alpha delta T, alpha delta T. Okay, so we have already covered this kind of questions, that what will happen if you go from equator to north pole of the temperature is increased, right? What will be the change in time period and all those things will be asked in this concept, right? Okay, now next is, as I told you, okay, right, change in thermal strain, thermal stress, which is basically delta L by L, right, which is alpha delta T. Okay, so this is the concept of thermal expansion, right? Right, everyone? Now, when you talk about the type of questions, so these are the type of questions. You can solve these kind of questions after the class. You can just use this as a revision, but think about it. What kind of question you can formulate? If you're able to think about all the type of questions that you can formulate, right, the concept will be easier. Okay. Now, after this, what would be the next concept? Think about it. Tell me, what would be the next concept? If you think about the same topic, right? So we can have the differential expansion. Tell me, yes or no, differential expansion, right? For example, we have solved a problem like when an object, right, is kept in some container and it is heated. So the container will also expand, right? The liquid inside that is also expand. So what is the net expansion? All those things, right, everyone? Okay. Now, even if that kind of problem is not that difficult, it is easy. Okay, because you will have to use the same concept, but what type of question can be asked? They can use the bulk modulus. Okay, they can use the bulk modulus, right? They will give you this pressure difference. Okay, and they will give you bulk modulus and they will ask you to find the change in volume, net change in volume, all those things, right? So if you see this, right, everything is written over here. Delta V by V, what is delta V by V? Tell me. I hope all of you remember delta V by V is volume strain, yes or no? Volume strain, right? And we know that pressure is equal to, or change in pressure is equal to minus B into delta V by V. Okay, so they can use this concept, right? They can use this concept along with your differential expansion. Okay, right? Got it? I'm just covering the concepts. I'm just covering the concepts. So I can say that just by like intuitive thinking, that if the change in volume of vessel will be more than that of the, tell me, will more than that of the liquid, right? Think about it. Then the level of liquid will decrease, yes or no? Think about it, yes or no? It's totally intuitive, right? And if the change in volume of container is less than that of the liquid, then it will increase. So there's no rocket science in that. And if it is same, then there will be no change. So that's what it is written in terms of gamma. That's what it is written in terms of gamma. Okay, right? Got it? Yes. Okay. Now there's one example based on this that you can just solve. Okay, right? So this was your thermal expansion. So when you talk about thermal expansion, that's the one of the easiest topic after calorimetry, where you can just use the formula, right? L is equal to L naught 1 plus alpha delta T, A is equal to A naught 1 plus beta delta T, or V is equal to V naught 1 plus gamma delta T, right? And the concept of properties of solid, which is stress strain relationship. Okay, that is quite easy, right? I hope all of you remember stress strain relationship. Yes or no? Hooke's law. Anyone who doesn't remember Hooke's law, please let me know. It is very easy. Okay, which is stress is equal to elastic modulus, right? Or modulus of elasticity into strain, and that modulus of elasticity is different from different kind of strain and strain. Y for longitudinal, right? G or sigma, right? Is for shear stress or shear strain, and B for volume strain, which is bulk modulus of elasticity, right? But all the three are almost same. Okay, now when you talk about mode of heat transfer, the most common that we will be studying is conduction, and this will be the easiest. Why? Because this will be same as electric current, right? I will use the analogous of electric current with this conduction. Okay, now convection and radiation, right? This is just basic formula that we'll be studying. We won't be discussing this in very detail, but the formula, right, of power radiated is very important, right? So after conduction, radiation will be the next topic, which you have to focus. Okay, so I hope all of you already know what is the meaning of conduction, convection, radiation. I need not to explain what is conduction, what is convection, what is radiation. Tell me. Yes, raise your hand. Right, everyone? Okay, so I'm just focusing on the concepts that you might forgot, or which is important. Okay, now when we talk about conduction, so conduction is just like electricity. Conduction is just like electricity. When you talk about electrical conductance, right, or conduction in conductors, right, sorry, electrical current, right? In the same way, when you talk about heat, thermal conduction, the energy, heat energy is passed on by one atom to another atom, right? By vibration. Yes or no? Tell me. Yes or no? Right? So almost everything is same. So I can say that, okay, heat will be conducted only when there's temperature difference. Okay, only when there is temperature difference. So I can say that the concept of potential, right, is associated with concept of temperature difference here, right? For example, when you talk about when you talk about electric current, so electric current flows from higher potential to lower potential. In the same way, heat will flow from higher temperature to lower temperature, right? So when you talk about Ohm's law, what was Ohm's law? Tell me, what was Ohm's law? V is equal to IR, right? Or I is equal to V by R? Yes or no? Tell me. So can I say that in the same way, heat current, right? Heat current, suppose dH by dt, heat current is equal to, right, thermal potential by thermal resistance. Think about it. Yes or no? Just use this concept. You don't have to study anything else. Just think about this concept. Yes or no? Right? Okay. Now, we have to know what is your thermal resistance, right? What is your thermal resistance? Because thermal potential is nothing but temperature difference. Am I speaking too fast? Tell me, guys. Am I speaking too fast? Okay. Now, think about it. When you talk about thermal resistance, okay, so let's see. This is the formula that we already have, which is Q by T, or in terms of instantaneous heat current, it is dQ by dt or dH by dt, right? Now, if you see this, what is this? This is, now minus is again the direction, because temperature is changing now. So delta T is negative. That's why we have a minus sign. Okay. Now, if you see this, delta T dt is your analogous to voltage. Now, apart from this, what we have? We have dx upon Ka. Yes or no? Dx upon Ka, right? So can I say that this dx upon Ka is nothing but R thermal? thermal resistance. Okay. Now, if we talk about average parameters, right? So let's talk about Q by T is equal to delta T by L into K. Okay, so this L is the length of the conductor, this A is the area of the conductor. What about this K? Now, if you relate the concept of resistance was what? Rho L by A, if you remember, right? Think about it. And in this case, this thermal resistance is what? Tell me, L by Ka, right? Don't you think that yes, right? There is the relationship, right? Doesn't matter what kind of resistance it is directly proportional to the length and inversely proportional to the area. And K is called as thermal conductivity, right? Because it is rho, which is resistivity, right? So 1 by rho is your conductivity. So it is a thermal conductivity instead of your, yes. So it is not actually 1 by rho, it is the analogous of sigma. It is the analogous of sigma. Got it? Right? Now, if you remember this, so all the concept of conductor or thermodynamic, sorry, this heat transfer to conduction will be easy, because now you can use Kirchhoff's law, now you can use series parallel condition. Yes or no? Tell me, yes or no, right? So let's see. Yes. So in steady state, as I told you, in steady state, this is a relationship. Okay, this is the relationship, which is Ka by L delta T. Okay, got it, right? Okay, now what kind of problem can be asked? I told you, just imagine this as your heat current. Heat current, okay, right? I hope all of you already know the unit and dimension. I need not to tell you about dimension, heat, and all those things. Okay, so I can relate it with total electric current. Whatever question can be formed in current, let's say, can be formed in heat, right? Be it Wheatstone bridge, be it your KVL, KCL, be it any loop. Okay, what will happen? Instead of giving you resistance, you will be given a rod. Okay, a rod of different length, different area. Okay, so see, right? This is your formula which I told you. Thermal current is change in temperature, which is thermal voltage difference, divided by thermal resistance, which is L by Ka. Okay, now let's try to think about the problems. For example, this problem. Now tell me, which concept can be used in this problem? Tell me, which concept of electric current can be used in this problem? Everyone, which concept? Can I use KCL here? Kirchhoff's current law, right? Junction law, yes. So I can say that the net current at this junction should be 0, right? Yes or no? So IT1 plus IT2 plus IT3 is equal to 0, right? And we don't know the temperature at this junction, so let it be T, right? So what is, and see again, either you take this direction or you take this direction if you're writing this. Okay, first of all, that's something I hope all of you already know, right? For our convenience, we will take either outward or inward, right? That's why we can write this, or you have to imagine that it is flowing in this direction and it is flowing in this direction. So you have to see what is the direction. So for the sake of convenience, I'll just assume that the direction of current is same in this only, right? Doesn't matter. So I can write it like this: 12 minus T by Ra, aluminium, I'll calculate separately, plus 50 minus T by R steel plus 4 minus T by R copper is equal to 0. Yes or no? Tell me. Yes or no? Right? Easy. So R aluminium, R steel, R copper, I can calculate using the formula R is equal to L by K. L given, K given, A given. You can calculate easily, right? Even if A is not given, right? And if it is said that A is same, then also you can just cancel out. Okay? Using this, you can find the temperature, right? Yes or no? Tell me, yes or no? This is your junction law, right? Okay. Okay, very good. Now, see, this is the same thing that is being done, right? The only thing is direction is taken as opposite that I have taken. Now, series and parallel. So see, what do you think? In this case, heat current is same. Heat current is same. So this is the junction, right? So this is the arrangement in which these two conductors, right? This conductor A and conductor B are in series, right? So if you talk about series, think about it. What will happen? Current will be same, yes or no? Tell me, current will be same? Now, we know that when current is same, then R equivalent in case of electric resistance, right? R1 plus R2. Yes or no? Tell me. Yes or no? Right? Right? Because potential difference is TH minus TC. Now, I hope all of you can use your KVL, right? And try to find the R equivalent in this. And surprisingly, the R equivalent will be same in this case also, right? In case of thermal resistance, it should be same now. So it is same in this also, right? So you can just club all the resistance and use it. You can just consider the surface, right? This arrangement like this, where this is your VA, VB, right? Instead of VA, VB, we have TA and TB, and resistance R1, R2, you can calculate using the formula. Got it, everyone? Tell me yes or no. Right? Now, that is the only concept that will be used in this topic, right? You don't have to use any other concept. If you understood this, then you can solve any problem in conduction. Doesn't matter what kind of mesh is given. Just use your concept of KVL, KCL, and you can use it. Tell me yes or no. Yes or no. Right? For example, just think about this problem. Just think about this problem. Okay. Now in this problem, we have this T1, T2, T3, T4. All of them are series and parallel. Tell me, all of them are series and parallel. Series, right? So calculate, yes, series. Got it, right? And the temperature is different, T1, T2, T3, T4, T5. Okay. So I hope all of you can solve this. Now next is parallel. When you talk about parallel connection, okay. So see, this is basically your series 1, 2, 3, 4, right? All in series. Okay. So equivalent is R1 plus R2 plus R3. Now parallel is again same as what we have studied in current. Okay. Now in this case, the temperature difference between the two endpoints of the slab should be same, right? The difference between the temperature difference between, because when we talk about electric current, the potential was same. Here the potential is temperature, so the temperature difference should be same, right? Got it? So we will use the same concept. Okay, in this current will be different and potential will be same. So I thermal from this, suppose we have this, right? So I thermal from this is equal to I thermal 1 plus I thermal 2. Okay, now just do this. If you do this, we will get this relationship. 1 by R current is equal to 1 by R1 plus 1 by R2. Got it? Right? Okay? Yes. So you can solve any problem like this. Now think about it. Think about it. I hope all of you can solve this problem now. Tell me, right? This series, this series, then parallel, then solve it. Okay? Right? Convert this in resistance. Doesn't matter. Right? Okay. Yes. Now there's one another concept which is based on the conduction, right? Okay. Now this is the temperature. What should the temperature difference? Okay. So that there will be development of ice at the center, and after what time, right? It will get solidified and all those things, right? Now let's start with our basic definition, right? Let's start with our basic equation, okay, of heat transfer, right? Now suppose the thickness of ice is x, right? And we'll take an elemental area dx, right? Okay. Now actually you just have to, this is for means student, not for even NEET students. Okay, but you can just see. We know that the heat transfer equation of heat transfer is this. Tell me yes or no. Yes. Okay. Now what we need to find? Tell me what we need to find. We need to find, right? Okay. What will be the time? What will be the time taken for ice to melt up to a certain thickness, right? Or in what time ice will be deposited and all those things. Okay. Now, suppose if the heat escaping through this ice in time dt is given by this, dq is equal to this. This is the basic formula. Okay, right? And when you talk about Ka by x, this is theta dt. So can I say that this dq is basically the heat transfer when this ice is converted into water? Yes or no? Yes or no? Right? And that is your latent heat of, yes, latent heat of fusion. Latent heat of fusion, which is ml, right? ml. Now mass is changing. Mass is a variable over here because as it is converting into water, right, the mass will continue to decrease. Okay, so you cannot take mass as a constant, right? So I have to continue. So basically this is dm, right? Now this mass will be rho into dx, right? Rho, which is volume, density, right, into area, because area will be same. I'm considering area as same, into dx, which is changing, right? Yes or no? So dq can be given by this. Now, if you equate these two, I hope all of you are following this. Now equate this and this. X will be taken this side, right? X will be taken this side. Okay. So you will get equation like this, right? You will get equation like this, right? And this is what we need. This is what we need. Okay. Because I want to know what will the change in thickness of ice in what time. Okay. Right. Okay, so after solving this, I'll get this equation, which is half rho x square by 2k t. It is t at a given temperature. Temperature is fixed, right? Okay, so this is the time taken. So the difference in time will be given by this. So I can say that the time taken is basically the difference of the square of the ice sheet, thickness of ice sheet. Got it? Yes or no? Got it? So this is what you have to use. So you can just write down this formula. Okay, Vishnu, density of anything is constant. Obviously, isn't it obvious that density would be constant? Think about it, Vishnu. Yes or no? This is the density of ice, na, right? This is the mass of ice. When you talk about ml, right? ये mass किसका लेते हैं हम लोग? Ice का ना. So this is the density of ice. Okay, got it? Okay. So yes, so you can just go through the problems based on this. Okay, you can go through the problem based on this. So see, these kind of questions are important, right? These kind of questions are important, right? Okay. Okay. So just go through these kind of questions. Now, when you talk about next mode of transfer, right, which is convection and radiation. So I hope, yes, everything is uploaded in the revision group. Everything is uploaded, right? More than enough material is uploaded. So please follow those materials. I have specifically sent all the material, that is materials, right? Please do whatever is told to you. Okay. I won't be discussing any other material, any other questions which is not told, right? Okay. Okay. So I hope convection, all of you know, right? Now, when you talk about convection, okay. So convection is basically more or like conductance, right? More like conductor, but the only difference is when you talk about conductor, in that case, the atoms is actually not moving from one place to another place. Yes or no? The atom is not moving from one place to another place. It is just vibrating and transferring its energy. But when you talk about convection, right? In convection, actually the atom which is having energy will move from one place to another place, right? Okay, got it. Now, this is the formula of convection current, right? This is the formula of convection current, right? And this will also depend on the area as well as temperature difference. Okay, but we won't be using this a lot, but you can just write down this formula in case if some question is asked. Harsha, see, because when you talk about convection, right, a particle is moving, okay, right? Now, when a particle is moving, right, it doesn't matter how long this is, okay, because when you talk about that I need to think also, right, Harsha, because even I didn't like think, but I just assume that it won't depend on length, okay, because particle is moving from one point to other point, so some parameters might get cancelled. That's why we have proportionality constant, okay, right? Because when you talk about this particle, so as it moves, yeah. So I'll just come back to that, right? Okay, because even I don't know that why it is not depending on that. It might be considered with this coefficient. It might be considered in that. Okay, right? Because we don't study convection a lot. That's why I never thought about that. Okay, yeah. And anyways, it's not in your syllabus, so no need to worry about that. Okay. The next is radiation, right? Next is radiation. Now, when we talk about radiation, okay, there are many concepts associated with radiation, right? So the first concept is the power which is radiated by any object. Okay. Now, I hope all of you already know about radiation. Tell me. Yes? So there are basic terms which are associated with radiation, right? Which are energy density, right? Spectral energy density, which is the energy density related with a specific wavelength, right? Then we have absorptive power. Now, these terms might be very confusing, right? So if you want to avoid confusion, just remember that this is what your term is, right? Okay, because we don't have enough time to discuss all these terms in detail. So we'll just be following the formula and how to use it. As simple as that, right? Okay. Now, just go through the terms that we'll be using. The first is energy density. I hope all of you know, right? Energy per unit volume. Then spectral energy density, which is energy density of a given length of wavelength, right? Or unit spectral region. Absorptive power, right? Or absorptive coefficient is basically the ratio of amount of radiation which is absorbed by the surface to the incident one, okay, right, which is basically Q absorbed by Q total, right? So since it's a ratio, it is unitless. Now, spectral absorptive power, it is basically spectral, again same, spectral absorbed power by total spectral power, right? Or it is basically monochromatic or for one wavelength, yes or no, Qa lambda by Q lambda, right? So it is same as this absorptive power. The only thing is it is for a given spectrum, right? Okay. Now, at a given spectrum, this, as we said, right, as we said, just use this formula and this formula. So if you use this formula, right, U is equal to U lambda by D lambda. So if you take the ratio, if you take the ratio by U, okay, because I'm saying Q, this is IQ. So can I say that this U, this A will be given as A lambda into D lambda? Okay, using this, right? If you don't get it, just remember that A is equal to A lambda into D lambda, same as this. U is equal to U lambda into D lambda. Okay. Now, emissive power is same as absorptive power, right? The emissive power is same as absorptive power, right? The only difference is when you talk about emissive power, it is the amount of heat radiated, right? When you talk about absorptive power, it is amount of radiation absorbed, right? And in the same way as we have spectral absorptive power, okay, d lambda is the change in frequency, sorry, change in wavelength, right? It is given for spectral region, no, for given spectral region, right? Means wavelength is changing. So if wavelength is changing, right, so we will have a differential this wavelength unit, okay? Got it? If you solve one problem, then you will understood, okay? Don't worry about that, right? Because this is very easy formula. You just have to, right, use this formula, okay? Now, when we talk about spectral emission power, it is same as spectral absorptive power. The only difference is instead of A, we will be using E as a parameter, which is your emissive power, spectral emission power. It is E is equal to integration of E lambda d lambda. Okay, got it? Now, after that, we have a term which is absorption, sorry, emissivity. Now, what is the meaning of emissivity? See, these terms you just have to remember, right? You just have to remember. Okay. Now, when you talk about emissivity, it is the radiation energy which is given out by unit surface area. Okay, right? So this is the radiation energy given out by unit surface area, and then we have relative emissivity, which is emitted radiation by any gray body divided by emitted radiation by ideal black body. So this is just a theory that we have to use. That's it, right? This is just as a theory that we have to study. Okay. Now, when you talk about black body, I hope all of you know what is the meaning of black body, right? Black body is a substance which will absorb all the energies and emit all the energies. Yes or no? Tell me. Right? This is what we study in black body. Okay. So I can say that for black body, right? For black body, it is one. For black body, it is one, right? Okay. So if for black body it is one, it means the ratio of E will be 0 to 1. Either it will emit completely, right? Or it will not emit at all. Okay. Right? So this is just a theory that you have to remember. Okay. Now these things you have to note it down somewhere and remember. Now just consider this as your light. Just consider this as a light. When you talk about light, right? So light, when it falls on any object, it will either get reflected or it will get absorbed or it will get refracted. Yes or no, right? Now, in the same way, right? Okay, in case of light, it is not absorbed unless and until you talk about photoelectric effect, but I'm considering that also. Okay, but in case of heat, heat energy, any substance can either absorb or reflect or transmit your heat energy or heat. So I can say that when you talk about the radiation, any radiation on any object, okay, it is divided into three parts: reflection, absorption, and transmission, right? So total energy is divided into three parts: reflection, absorption, transmission. If you divide it by Q, so you will get this relationship. Yes or no? Tell me, right? What is QR by Q? Tell me, everyone, what is QR by Q? QA by Q we have studied, right? This is absorptive power, sorry, absorptive coefficient. In the same way, QR by Q is your reflective coefficient and this is your transmittive coefficient. Okay, right? Not power, coefficient, because of the ratio, right? Okay. Right? So the sum of all the coefficients should always be equal to 1. I hope all of you are clear with this. So can I say that the ratio, any of the ratio is between 0 to 1, right? Okay. Yes. So, and if any one of the ratio is 1, which means the other two should be 0. Okay. So I hope all of you are clear with this concept. Okay. Got it? So reflective power is again divided by, sorry, multiplied by 100%, right? Okay. So you can go through the problems. Okay, you can go through these problems, right? Now, the next is ideal black body. So it is just a theory that we have already studied. What is the meaning of ideal black body? It means, right, it will absorb as well as radiate, right, all the energy. Yes or no, right? Means it will absorb, yes, it will absorb all incident radiation and it will emit all absorbed radiation, which means A lambda will be 1 as well as ER will be 1. Okay, got it, right? Okay. Now, in this, we have one law that you have to remember, right? Okay, which is the ratio for any body, right? For any body, okay, at a given temperature, the ratio of spectral emissive power to the spectral absorptive power is constant, right? Okay, is constant. And that constant is called as emissive power, spectral emissive power, okay, right? This is one law which is called a Kirchhoff's law. You have to remember this. Okay, so obviously it is in E lambda by A lambda, right? Spectral emissive power by spectral absorptive power is equal to, right? Tell me a constant which is spectral emissive power of black body, right? Do not get confused by this and this. Okay, so this is the spectral emissive power of ideal black body, right? Okay, now if this is the constant, if this is constant, then you can use this at temperature T1 is equal to this at temperature, right, T2. Okay, so you can use this, right? Okay, so using this, can I say that since it's a constant, a good observer, if E lambda is more, then if E lambda is more, then A lambda should also be more, right? And if E lambda is less, then A lambda should also be less, right? So good absorber is also good emitter and bad absorber is also a bad emitter. Okay, right? Okay. Now, next is very important, especially for NEET. Okay, right? This question is asked, this concept is asked a lot, which is Stephen's law. This is for NEET and JEE both, right? Many questions is asked based on this, right? So we won't be deriving this formula at all. We'll be just using the formula, which is E is equal to sigma T to the power 4. And if you talk about Q, right, this is EA sigma T to the power 4. This is the basic formula. EA sigma T to the power 4. Yeah, this one, right? This is, sorry, this is power, right? Q by T, Q by T. Okay, got it, right? Okay, now when you talk about ideal black body, E is equal to 1. Okay, E is equal to 1. So that's why, and A will be this side. So that's why we have SIF, we have only sigma T to the power 4. Okay, so in this, you just have to remember that the amount of radiation of the power, right, is directly proportional to T to the power 4. Okay, got it, right? Okay, now what kind of question can be asked in this? So if I'm having two different temperatures, suppose if I'm having two different temperature and I want to find how much energy, right? How much power is radiated from one at one temperature to other temperature. So you just have to find the difference, right? Okay, so the rate of heat transfer, the rate of heat transfer is nothing but the amount radiated at temperature T1 minus amount radiated at temperature T2. Tell me yes or no, right? Okay, okay. So this concept is quite easy and the problem that you have to solve is just formula putting getting. nothing more than that, right? You will be given, if you talk about the parameters, right, either you will be given the rate of heat transfer, this, right? Now what is the difference between this and the conductor one? Tell me. I hope all of you remember, when you talk about conductor, it is dq by dt is directly proportional to delta t, yes or no, right? But in this case, dq by dt, right, is basically not delta t, it is t1 t2 to the power 4 minus t1 to the power 4. Okay, it's not delta t to the power 4, right? That's wrong. Delta t to the power 4 is not correct. Okay, that you have to understand, right? Got it? Okay, I hope all of you understood this. Tell me, I hope all of you understood this. Okay, so this is the rate of heat loss. Now, if heat is lost by some object, think about it. If we have an object, if it is releasing heat, then the temperature of this object is going down, yes or no? Tell me, the temperature of this object is going down, right? And when you talk about this substance, for this substance, right, Q is basically ms delta T, yes or no? Because it is losing heat, na, right, using calorimetry. Now, can I see that for this object, the change in heat is ms, right, dt by dt, okay, right? Now, I'm just considering one random example, right? Okay, they might have some other constant. So I can say that for this temperature, for this object, the temperature is falling down if it is releasing or if it is radiating heat, and then the rate of this change in temperature is given by, right, sigma A divided by msj. Now J is a constant, it will be given in the problem, okay, into T to the power 4 minus T naught to the power 4. This is your Newton's law of cooling, yes or no? Tell me. Not Newton's law of cooling actually, right? Newton's law of cooling is comparative difference, okay, right? We'll see that also, but yeah, it is basically the cooling of the substance when it is radiating heat. Yeah, even I don't know why they're using it. Okay, anyways, it depends on the problem. If in problem it is given, then you can use, otherwise you can just leave it. Okay, got it? Okay, so I hope all of you understood this concept, yes or no? Tell me, I hope all of you understood this concept. Right, everyone? Now this concept is important, right? This concept is important, so you should practice some problems based on this concept. Special needs students, many questions is asked based on this concept, okay, right? And need students, I have already given you the numbers, okay? Please try to go through all those questions, okay, without fail. See, this question is asked here. So while revising, just go through the problems based on this, okay? Now, Newton's law of cooling. What is the meaning of Newton's law of cooling, right? This is the concept that we just discussed. Now, the only thing is, when any object lose energy, it will cool down, yes or no, right? Suppose any object, I'm talking about any object. We have an object over here, right? And the temperature of this object is T1 and the outside temperature is T2, okay, right? Right? And it is losing energy. Obviously, it will lose energy if T1 is greater than T2. Yes or no? Tell me. Right? So if it is losing energy, right? And see, we saw the same case in radiation, but in this case, I'm not talking about radiation. I'm just talking about, right, this normal process. Okay. So can I say that? Can I say that, right? This amount of heat which will be released, okay, will be the amount of heat which is lost by this object, right? That we have already discussed in the above expression. So the amount of change of heat in this object is given by dq by dt, right? Which is basically ms delta t by dt. Yes or no? Tell me, yes or no? Okay, so the rate at which this object is cooled down will depend on the rate of change of temperature of this object. Okay, right? Right? Any issues? Tell me. See, capital T was temperature, small t was time. Okay, right? That's it. Instead of theta, I'm using t. I just wrote the same expression, right? Okay, now this is one of the important concept for NEET students, right? 3-4 question as asked in your NEET examination for JE also, right? This question, especially this expression, right? There are many problems based on this expression. Now think about it, right? Suppose I'm having an object of temperature theta. This is the temperature of object, right? Temperature of the body. And the surrounding temperature is this theta naught. So what is the difference in temperature? Tell me, what is the difference in temperature? Right? It is obviously theta minus theta naught. Yes or no? Theta minus theta naught, right? Okay. So suppose after heat exchange, right? After heat exchange, there will be some another temperature theta, which will be the equilibrium temperature. Think about it. Yes. Yes. So by Newton's law of cooling, I can say that the rate of change of temperature is directly proportional to this difference in temperature. Okay, the difference would be more, the rate would be more. Makes sense, right? Makes sense now, right? And you don't talk about this negative, because negative is just the indication that it is cooling. The temperature is decreasing, as simple as that. Okay, right? Now, this is something that we got from approximation. What we got from approximation, let's see. So suppose we have temperature of body, right, at theta 1, and it's decreasing from theta 1 to theta 2. Okay, right? For body, just of body. So initial condition is theta 1. Outside it is theta naught only, because obviously when you talk about surrounding, the temperature surrounding will not decrease. Yes or no? Tell me, right? Whenever we solve any problem, we assume that the temperature surrounding will not decrease, right? It will be same. Yes or no? Right? Constant. So this theta naught is the temperature surrounding. Now suppose after time t2, suppose after some time, this temperature of the body becomes theta 2, becomes theta 2. The outside will be theta naught only. Yes or no? Tell me, yes or no? Right? Okay. So I want to find how much, yes. Okay, so I want to find, right, what is the average change in temperature? Think about it. What is the average change in temperature? Think about it. So see, this is theta 1 plus theta 2 by 2 will be for object, na? It will be for object, right? Okay, but I'm talking about the change, right? So minus theta naught, which is the outer temperature, right? Theta minus theta naught, na? Okay, so if you just use this expression, if you use this expression, right? Okay, so I can say that this d theta by dt, d theta by dt is equal to, or minus d theta by dt is equal to constant k theta minus theta naught, right? And this theta is the average change of the temperature of the object. Got it? Tell me, got it? Tell me. right? So this is the expression that we will get. So you just have to use this expression, okay, this expression. Okay, got it? Unless and until it is variable. If it is variable, then you have to use differentiation integration. Okay, then you can use this one. If theta is given in terms of time or something like that. Okay, that is your advanced level problem. Okay, everyone, right? So everyone need to remember this. I hope all of you are clear what is theta 1, what is theta 2, what is theta naught, right? So let's see one example. This type of problem is asked a lot, okay, especially in mains and NEET. Now, see, this type of problem will be asked, right? Suppose in 30 seconds, right, 80 degrees to 70 degrees centigrade, okay, and 70 seconds from 60 to 50. Okay, right? Find the room temperature. So theta 1, theta 2 is given. Theta 1, theta 2 is given at T1. And then theta 1 dash, theta 2 dash is given T2. But find theta naught. Easy formula putting getting. Can you find it? Tell me, can you find it? Yes? Yes, very good, everyone. Okay, very good. Now, this is the concept of Newton's law of cooling, right? Now, tell me, what will be the limitation of this? Tell me, what will be the limitation of this? So the first limitation is the temperature difference should not exceed 35 degrees centigrade, right? The temperature difference should not exceed 35 degrees centigrade, right? And we are assuming that the heat of it should only be radiation. It is not conduction or convection. Okay, got it, right? Okay, so these two are the limitations. So basically, the limitation that we need to remember is this one, because obviously, if it's conduction, we are like we know enough that we should not use this concept at all, right? Because then it will be become half question of heat transfer, right? Got it? Tell me. Okay. Now, those who want to derive it, you can just see this formula, but I am not going to derive this one. Okay, it is clearly understood. Okay. So instead of that, you just remember this. Okay, you need not to derive it. No, no, Harsha, it is not applicable. Because see, why we are doing it, if you see the derivation, we are assuming this, we are assuming the all the upper levels as constant, we are removing this, okay? We are assuming this as less than 1 and we are removing all the other higher order, yeah. No, in long formula you can use, right? But see, we are not using long formula, now we are using only the approximated one. If you see this, we see the over derivation, right? We are just taking the lower order terms, the higher order terms that we are considering, right, is negligible or zero. Got it? Got it, Harsha? Right? So that's the reason. So just remember this. For advance, you have to use this main one, okay, for advance. Okay. Now we have, yes, so next we have something called spectral energy distribution curve for black body radiation, or Wien's displacement, Wien's displacement law, right? Okay, so basically, what is Wien's displacement law? Now, according to Wien's displacement law, okay, the wavelength. Now think about this. Think about this. If wavelength is more, energy will be less or more. Tell me. If wavelength is more, energy will be less or more. Less. And if energy is less, what about temperature? What about temperature? Prashant, it's inversely proportional, na? Lambda more, energy less, right? Got it? Yeah. So can I say that? Can I say that if for any spectral radiation, for any spectral radiation, as we increase the lambda, okay, right, it will try to increase up to some temperature, okay. The intensity, the spectral radiation intensity will try to increase up till maximum temperature, okay. After that, will start reducing, okay. This is your yeah. So this is your spectral energy distribution curve of black body. Means you cannot increase the temperature of any object, right, beyond certain temperature, okay. Now think about it, how that is possible. Think about it. Just take example of your iron rod. Just take example of iron rod, right? Just for black body, I'm just taking example, right, to let you visualize what happens. Suppose you heat something, right? Suppose you heat something, so it will heat up, yes or no? It will heat up, right? But after some point, it will become so hot that it will start radiating. It will become a source of heat transfer. Yes or no? It will start radiating, right? So I can say that, yes, after red hot. So I can say that, okay, after some point, it will not, right? It will not increase the temperature, right? The extra energy that you're providing, it will be radiating in terms of heat. Okay, think about it like this. Okay, I'll just give an analogous. Okay, it might be true, it might not be true. I'm just giving an analogous to understand this curve. Okay, because I haven't, frankly, done a lot of research on this, right? So this is the topic which is asked like very rarely. That's why I haven't, like, frankly, even I didn't research a lot on upon this. We just have to use this formula, right? Okay, whenever a question is asked, we just have to use this formula. Okay, that's it, right? We already know that this is your total emissive power because it is the area under E lambda and D lambda curve, and we know that total power or total emissive power is given by, wait, what happened? Yeah, E is equal to E lambda D lambda. Yes or no? Tell me. Which is area under this curve, right? And when you talk about radiation, this is directly proportional to T to the power 4. Yes or no? Okay. So if you club these two, let's think about it, right? Let's club these two. So we know that E lambda D lambda integration 0 to infinity is equal to E, which is sigma T to the power 4, right? How this is there? Because E is T to the power 5 and integration of D lambda is 1 by T. So TT will get cancelled, right? So we'll get this. Okay, got it? That's it. So this is what we have already studied in Stephen's law, right? Okay. So what you have to remember here, that spectral emissive power, the spectral emissive power is basically directly proportional to T to the power 5. Got it? Yes or no? Got it? This is something that you have to remember. Okay. And lambda is inversely proportional to T. This is from Wien's displacement. Okay. So this topic is of low importance. Okay. Right? You can just remember the formula. That's it. Yes, height of the peak is maximum wavelength. Okay, height of the peak, right, is your maximum emissive power for given wavelength, right, at a given temperature. Prashant, as I said, that is your Wien's displacement law. Okay, no, listen, right, as we said that we know that the maximum wavelength, right, as you keep on increasing, the wavelength, there will be a peak, which means at a given wavelength, the temperature would be maximum. Okay, right? Okay, so I can say that for maximum emission of radiation decreases with increase in temperature. Okay, after some certain wavelength. So lambda is inversely proportional to 1 by T. Okay, or lambda T is equal to constant B. Right? This constant is called as Wien's constant. And it is not T to the power 6, it was T to the power 5. Okay, it was T to the power 5. Okay, see, this is, in this you are just asked to find basic formula putting getting, where you just have to take the ratio of lambda and T, as simple as that, right? If you see the previous question, I have given you some numbers. Okay, the only question that will be asked is the ratio of lambda with temperature. For example, this problem. Okay, okay, got it? Okay, next is calorimetry. So I hope all of you already know calorimetry. Heat loss is equal to heat gain, conservation of energy, right? For temperature change, we have ms delta T, right? For latent heat, we have ml. That's it. So go through that. Molar heat capacity, all the things that we have already studied in chemistry. CPCV, I hope all of you already know this. So I'm not going to cover this topic. Okay, because everything is already covered in chemistry and we've already studied these things. Do I need to cover this? Tell me, guys. Do I need to cover this? I don't know what is international calorie, Manoj. Google it. What can be international calorie? I haven't heard the word international calorie yet. Until you told, I didn't know what is international calorie. Leave it, na. No, no, it is just for your revision for thermodynamics. Okay, that's it, right? Okay, the next is KTG, kinetic theory of gases. Now, this portion is same in physics as well as in chemistry. I hope most of you already remember whatever we have studied in chemistry. Yes or no? Right? The assumptions, the postulates, right? And in physics, we just have to talk about the velocity and Maxwell distribution curve. Okay, right? So tell me, I hope all of you remember the postulates of KTG, the assumptions. Yes or no? The volume, tell me, right? Okay, so I'll be skipping those things, right? I'll be skipping the concept of ideal gas, real gas, and all those things, because I hope everyone at least remember these things. Okay, equation of ideal gas, PV is equal to nRT, how to use ideal gas equation, and all those things. It's same, gas law, Boyle's law, Charles law, right? Just go through it. If you have any doubt, you can ask, but I'm assuming that all of you have already gone through this and you will cover this in chemistry anyways. So I'll be skipping these things. Okay. Okay. The thing that we need to worry about, or the topic that we have to study, is your velocities. When you talk about velocities of gases, right? We generally talk about three kind of velocities, right? First is mean square velocity, right? Second is most probable velocity, right? Okay, so we have RMS, most probable, and average velocity. Average velocity. Okay. Now, when you talk about RMS, so what's the meaning of RMS? It is roots mean square velocity. Now, suppose when you talk about any molecule, okay, any molecule can travel in any of the direction, X, Y, Z, right? And root mean is not a term just for velocity. Root mean is a term which is just like average or most probable of any physical quantity, any physical quantity, right? Suppose I'm having physical quantity Q, right? So for physical quantity Q, its RMS is equal to root of Q1 square plus Q2 square plus Q3 square. Okay, got it, right? For average, suppose you have function f of x, right? Okay, or f of t, suppose f of t. So the average of this is integration of f of t dt 0 to t divided by integration of dt 0 to t. I hope all of you know this. Tell me. I hope all of you know this. So these are the standard definition of this average and RMS. Okay. Now I was saying, suppose I'm having any object which can move in any direction, x, y, z, right? So the velocity is given by this vx plus vy plus vz. Okay. Now if I want to find the RMS value of this, so the RMS value of this v, since it has three different velocities, vx, vy, vz, in this three axis, right? So it is what? Tell me. And I'm assuming that the speed, this magnitude of vx, vy, vz is equal. Okay, is equal. So can I say that it is root of vx square plus root of vy square plus root of vz square, right? And since vx is equal to vy is equal to vz, it will be taken as common. So we will get vz root 3. Got it? Any issues? Any issues? Okay. Now we will relate it with your change in momentum, then pressure. Okay, right? Then we will use Adidas equation and use of KTG, which is, tell me, kinetic energy is equal to half mv square is equal to, I hope all of you remember, 3 by 2 kT. Yes, right? By using this, you can find the velocity, RMS velocity, okay, which is root 3 kT or 3 RT by m, right? Okay, now since you're not in class 11th, you don't have to worry about derivation. You just have to remember the basic formula, which I hope all of you already remember, right? Okay, yes. So the basic definition of kinetic energy, average kinetic energy, this is average kinetic energy, is 3 by 2 kT. Now this 3 by 2 is for monoatomic, if I remember, monoatomic, right? Because this is actually a degree of freedom, which is F by 2 kT. Now when you talk about kT, it is for per molecule. Per mole, it is, tell me, it is RT. Got it? I hope all of you already know these things. Okay, very good. Now, in the same way, most probable speed, right, is the speed of maximum number of molecules. Suppose I'm having 100 molecules. Out of that 100 molecules, if 60 molecules having speed of, suppose 50 meter per second, right? Okay, 30 have 40 meter per second. So not 40, 45. And remaining 40 is having, suppose 60 meter per second. Suppose I'm just giving a random number, do not get calculate, okay, right? Now then this is your most probable, which is the median, right? Or the, sorry, the mode of all the velocities, right? Maximum number of speed of maximum number of particles, okay, is your mean most probable velocity. Now average of every velocity is your average velocity. Now when you talk about the formula is quite simple. You just have to remember these formulas. Wait, I'll just show you. Okay, so I hope all of you remember this. I'll just write it down. Okay, VRMS is equal to root 3 RT by M. V average is equal to root, tell me, 8 by pi RT. And V most probable is equal to root 2 RT by M. Got it? Right? Okay. Okay. Now next is degree of freedom. Now, as I said, depending on the type of molecules, we have different degree of freedom. Okay. So basically, degree of freedom is divided into three parts, right? Translational, vibrational, and rotational, right? Okay. So we need not to worry about lots of things. We just have to know how many degree of freedom are there in translational, how many of are there in rotational, and how many of are there in vibrational. Okay, so we will have a table in chemistry. I hope all of you remember that the translational degree of freedom is just 3. Either any body can move in x-axis, y-axis, or z-axis. Yes or no? Right? So we have maximum 3 degree of freedom for translational. Now rotational, okay. So rotational depend on the structure. Either it is monoatomic, diatomic, triatomic. Vibrational, right, which is exhibited at a very high temperature, is also of 2 types depending on the structure only. Okay. So this is the table that I was talking about. Now, if you talk about monoatomic, right? Monoatomic, one atom. So monoatomic can only move this direction, right? X-axis, Y-axis, Z-axis. So it will have only 3 translational degree of freedom. It won't have rotational, right? Or vibrational. We won't talk about vibration because it is at the vibration will only be at very high temperature. Now, when we talk about diatomic, think about it. It can see it can move in x-axis, y-axis, 3x, z-axis. So translation will be 3 for all the type of molecules. But when you talk about rotational, think about it. Now, since it cannot rotate along its interatomic axis, which is suppose it is x-axis, it cannot rotate around x-axis, but it can rotate around y-axis as well as z-axis. Yes or no? Tell me. Yes or no? Right? So it will have 2 rotational degree of freedom. Same with triatomic, right? And polyatomic, triatomic, nonlinear polyatomic can rotate in direction. So we will have 3 degree of freedom for that. Okay. So this you have to remember. Okay. Right. Wait. Just what axis? No axis. You don't have to remember. Just remember the degree of freedom. That's it. Right. So after that we have thermodynamics. Right. So I hope all of you remember this Boyle's law, Charles law, right? Gay-Lussac's law. Right? So I'm not going to teach these things. Okay, I'll be moving to thermodynamic processes now. Okay, got it? Okay, now before moving that, we have a last topic in KTG, which is your maximal distribution curve. Now, this is just a diagram that you have to understand. Now, if you see the diagram, right? Suppose you have a system of gases, right? A set of gases, suppose 100 molecule of gases at temperature 50 degrees centigrade, suppose. Now, if this 100 molecule of gases I'm considering, so in this, the highest fraction of molecules will have speed, which is most probable speed, tell me. Yes or no? Right? And we know that V most probable is less than V average, is less than V RMS. I hope all of you know this already, right? From this expression. Okay, right? Now, so we will have V average somewhere over here. I'll just use a different pen. Somewhere over here. V average somewhere over here. Because the fraction of molecules having average speed will be less than that of the most probable, and the fraction molecule having RMS speed will be even lesser, right? Now, what do you think? If we increase the temperature, what will happen? Think about it. If we increase the temperature, what will happen? Don't you think that the overall speed will increase? Right? The overall speed will increase. Now, initially, suppose we have V most probable, okay, V most probable as 50, V average as 55, and V RMS as 60, okay, right? So at temperature T1, at temperature T2, all the velocities will increase, right? And right now, after increasing, what happens? Suppose this is in number it is 60, in number it is 30, and number it is 10, suppose, right? Okay, but after increasing temperature, who knows, it might change, right? Because all the molecule is increasing, right? Also, the energy of all the molecules is increasing, the temperature of all the molecules is increasing. So the number of molecules having most probable speed will decrease. it will become 50, right? Now this might become 35 and this might become 15. Yes or no? Tell me, yes or no? Think about it. Now, if I observe the same thing in the curve, right? So the curve will flatten, curve will try to flatten, okay, right? And the peak will go down. Got it, right? See, so as the temperature increases, the Maxwell distribution curve will flatten and the peak will go down. That's it. That's the whole thing that you have to remember. Okay, got it, everyone? Prashant, as I said, as temperature increases, right? Since area should be constant. What is the area? Area is the number of molecule. It's constant. The number of particles having most probable speed will be less, will decrease, right? And since the number of particles, the number of molecules having most probable speed will decrease, the curve will flatten, right? The peak will go down, right? The curve will flatten as the temperature increases. Got it, Prashant? Okay, right? Okay, very good. Okay, now after this, we just have to use, yeah, we will start thermodynamics. Now, as I said, this is same as your chemistry one. So I hope all of you know what is system, what is surrounding, what is homogeneous system, what is heterogeneous system, and all those things. So I need to teach about those things. Okay, what is process? So I'll just go to the basic concepts. Okay, right? I'll revise those. Now, when you talk about the processes, we are two type of processes, which is reversible and irreversible, right? Okay. Now, in this case, we won't be talking about reversible, irreversible. That is in chemistry. Okay, right? In this, we just have one. Now, sign convention. Now, think about it. What is the difference in this and this? There is no difference. The only difference is when you talk about chemistry, right? We talk about when you talk about work done, it was work done on the system, okay, in chemistry. But when you talk about physics, in physics we will take work done by the system. Got it, right? Otherwise there is no change. Okay, don't remember positive negative, just think like this, because if you remember positive negative you will get confused, because in some cases in chemistry also it will be given work done by the system. Suppose you give work done by the system, right? Then the formula will be same as the physics one. Got it, right? Because if I'm talking about P delta V minus, okay, it is in chemistry. If you remember, it is in chemistry, yes or no? But you have to remember that this was P external, right? But in physics, it is P internal into delta T, sorry, delta V, work done. Now, is there any difference between these two? Think about it, right? There's no difference between any of the formula. Okay, the only thing is, right, what we are taking, either internal or external. Got it? So sign convention is same, everything is same, the only thing is work done, right? If you understood this concept, you will not make any kind of mistakes, because sometimes in physics also, instead of giving work done by the system, they will give work done on the system. So obviously you have to use minus over here, yes or no, right? Because it is f dot dx, f dot dx. If force is along the distance, it will be positive. If force is opposite to the displacement, it will be negative, as simple as that. Okay, okay. Now, okay, it's already one. So I'll just try to, okay, it's already one, right? We already have time. So you have class at 2 o'clock also, right? No, chemistry, there's separate section. Chemistry will be separate for NEET and JEE. Okay. So for NEET, chemistry is from 2 o'clock. For JEE, okay. So I'll take just half an hour. So NEET students, if you want to go, you can go. We will cover this in next 3:45 if we get time. Okay, right? So see, I'll just try to cover some basic points, which is about adiabatic process. The formula would be same, right? I'll just cover this. Now, when you talk about first law of thermodynamics, okay, the first law of thermodynamics will be same. The only difference is when you talk about first law of thermodynamics, okay, in chemistry, since the work done was on the system, okay, we have internal energy as Q plus W, yes or no, right? But in physics, Q is equal to internal energy plus work done, right? That is the only difference, because here work done is by the system. Got it? Okay.